So a neutralization reaction is one of the three subtypes of double replacement reactions. Remember, there were precipitations. So the precipitation, those are the color change. We saw a lot of those. And neutralization is when water is the product, and this water is a liquid, and we can't see the formation of the liquid. But what can be detected is a temperature change. And so that was in the double replacement reactions lab. And so water comes from the reaction of an acid with this base. And the acid always will contain the hydrogen cation, and the base will always have or produce the hydroxide. So what's formed is this water that is due to the double replacement where the hydrogen bonds to the hydroxide and you end up with HOH, which can be written as H2O. It's one of the only times you can break into the polyatomic ion parentheses. So you have water, and also this is a salt. So NaCl is a table salt, but in general, any ionic compound can be called a salt. So this is in the neutralization reaction. You have the hydrogen ion from the acid combining with the hydroxide ion from the base, and then you end up with the water molecule. So this ends up being HOH that you can write as H2O. And the other product is an ionic compound. So this NaCl is table salt, but the general term salt works for any ionic compound. To look at neutralization reactions is by using the complete ionic equation and a net ionic equation to see exactly what changes in the reaction. So this is the complete balanced equation for a neutralization reaction where you have hydrobromic acid, that's HBr, and you have barium hydroxide, that's BaOH2. And this is written as the complete balanced equation. So there's coefficients. The 2 balances out the hydrogens, which you should also notice that there are hydrogens in OH2. So it's useful to write H2O as HOH in the balancing. So you can see that there are 2 hydrogens and then there are 2 hydroxides. So 2 hydrogens and 2 hydroxides. Because sometimes that 2 subscript in H2O gets confusing because it's hard to remember. There's a hydrogen in the acid and also a hydrogen in the base. Okay, and then you can also see that there's a 2 for the bromines, and that coefficient is covered with HBr. So this is a complete balanced equation, but what's more useful is the complete ionic and net ionic equation when understanding exactly what's changing in this neutralization reaction. So the complete ionic equation shows aqueous ions, which basically means you take any aqueous solution, so any aqueous solution that has the subscript AQ can be split apart into its ions. This HBr is an aqueous solution, BaOH2 is an aqueous solution, and BaBr2 is an aqueous solution. So these aqueous solutions can be split apart into the ions, and this one, which is liquid, cannot be split apart into the ions. Okay, so anything that is aqueous gets split apart into the ions. So this is HBr. This is written as the H plus ion and as the Br minus ion. So notice it is the ion charge values that are shown in the ionic equation. So we don't normally get to show those ion charge values in a balanced equation. Okay, so the complete ionic equation does have the plus and minus signs. So this is an aqueous solution, BaOH2, and this is the barium ion, and you'll notice that this is a +2 charge. That's because it comes from this subscript 2 that picks up and becomes a +2 charge on the barium. That 2 also becomes a coefficient in front of the hydroxide ion, because that's what that subscript indicates, that there were 2 of the hydroxide ions that balanced out with the +2 charge of the barium. So this breaks up into the 2 hydroxide ions and the 1 barium ion. This aqueous solution of BaBr2 breaks up into the barium ion, which notice has the +2 charge. That comes from the 2 subscript that became a +2 charge. And then this 2 also becomes a coefficient when this breaks up into the bromide. So there were 2 Br- ions that balanced out the +2 charge of the barium. That ionic equation starts with the complete ionic equation. So I've cleared this so we can see this complete ionic equation that shows the aqueous ions. And then the net ionic equation removes any of the spectator ions. So no spectator ions. And the spectator ions are the ions that are unchanged. So like a spectator at a sporting event, a spectator at a sporting event doesn't participate in the sport. The spectator's just there and watching it. So the spectator ions from the complete ionic equation are the same on both sides. They're not changed. So they're the same on both sides of the reaction arrow. So we can find the ones that are the same on both sides of the reaction arrow. Then they have to be exactly the same. Okay, so this is an example. This is the same bromide ion that's aqueous and has the coefficient 2. So when I mean exactly the same, it has to be the same with the aqueous physical state and the same coefficient. It has to have the same numbers on both sides and the same element. So this is the barium ion. This is Ba+2 with the aqueous. So same charge, same physical state. And so that's exactly the same. You can actually get rid of those, getting rid of those spectator ions. And what you're left with is this that carries through is the hydrogen ion becomes part of the net equation. This hydroxide ion becomes part of the net equation, and this 2H2O liquid becomes part of the net equation. So you just carry everything down, and this is what occurs. This is the neutralization reaction, which is the formation of water, and this is basically the main event. That hydrogen has combined with hydroxide to form water, and all those other ions are present, but they are not participating in the reaction, and so they can be removed in the net ionic equation. So no spectator ions in the net ionic equation.